Same way, there's a correlation formula if this data becomes large correlation. And there are some other measures that we can use to see if two vectors are similar or not. Okay, so the point I'm trying to make is, once we have picked out, so once we apply this LOG, this will give us hundreds of points, depending on our threshold. Because if the gradient is above, the Laplacian is above a certain value, we are considering that particular xy as a potential feature. So this will give us hundreds of possibilities, right? Once we go to this part, it will remove maybe 50% or maybe 60% of those, because not everybody appears as we zoom in or zoom out, okay? Then as we go to the rotation part, and we rotate and see, is this still being recognized? We'll end up, so over here, by the time we are done with this step, we will be left with, a few dozen features. Then we will go to each one of those and further attach a descriptor for the purposes of later on be able to match that this corresponds to the exact point through some measure, which could be Euclidean or whatever the case may be, okay? So in short, SIFT and SIRF. If I remember correctly, SIFT produces like 128 value descriptor for each feature. And this produces a 64 value descriptor. So anyway, one more small clarification before we take a look at the PowerPoint slides is, how do we know a feature is scale invariant? Okay, so let me clean up a little bit. Okay, so scaling, as you guys have already seen once we did the transformation matrix, right? We talked about the scale being S cosine theta minus S sine theta and so on, right? So S was our scale, meaning how far to zoom in or zoom out. Okay, so if you are given an image, butterfly or whatever the case may be, okay, we want to zoom in, zoom out, and then see. So we may compute a feature over here. Then, for example, we zoom out. Okay, then we compute the same Laplacian of Gaussian over here. Let's pretend this one shows up in our threshold, but this disappears. Okay, so how do we accomplish that? Okay, I gave you a hint some time ago. The effect of zooming in, for example, let's say you have a tree with all the leaves.
And then you zoom out, it becomes blurry.
Exactly.
Out of focus.
So if you were to artificially create the effect of looking at a tree from a distance, what would you do to this image?
Apply an average.
Or what's a more controllable filter? Which will, yes, the Gaussian. So if we apply a Gaussian to a tree, right? To show you in the beginning, okay, for example, we apply Laplacian or Gaussian, it's recognizing big changes here. Let's pretend it's recognizing these are the features, okay? Now we apply a Gaussian blur to it. Meaning, apply a Gaussian kernel. We pick the sigma, whatever, right, to create the, and now this will start to become more hazy, correct? But still, some of the leaves will show up, some will disappear, okay, depending on how much blur did we do. So then, let's pretend these disappear, out of these four, the outside ones still were recognized. Okay, but the inside one got blurred with the others. So as we do Laplacian or Gaussian, they disappear. So in our sift or surf approach, as you can see, we will eliminate the inner two feature points. We'll only keep the outer feature points. Okay, so that's how. So scaling, basically, what I'm trying to say is accomplished via Gaussian kernel. Okay, so with respect to scaling, there's also a concept of octave. Octave basically means doubling or having the cutting the image in half. So, for example, in the SIFT algorithm, as an example, what they do is they use 4 octaves and 5 blur levels. Okay, by 4 octave basically means is this image will be reduced in half the size, then further half, then further half. Each time we reduce it to half size, we apply 5 Gaussian kernels. Okay, and same 5 Gaussian over here. So anyway, the authors came up with a pretty robust scheme. Again, the whole goal is we want to make sure only those features are kept which really are still visible to us as we zoom in, zoom out. So basically, octaves with the Gaussian kernels create the nice effect of zooming in, zooming out at different ranges, basically. So that's the idea. Okay. Now let's take a look at the algorithm. And hopefully now it should start to make pretty good sense. Okay, so like I was saying, this handout is already on the website. This is from, I think, University of Utah or someplace. I thought they did a good job on summarizing the algorithm. Okay, so let's take a look at SURF. SURF is the faster version of the very famous SIFT algorithm. Okay, in the beginning it was not patented, then they patented it. Anyway, so there are 4 steps to it, as we discussed on the board. Feature detection. Can you guess what technique will we use for detecting potential important points on an image? Laplacian or Gaussian. Scale space. Basically create Gaussian blur and eliminate those features which don't show up at different scales. Then rotation invariance will further apply some kind of a rotational mathematics over here so that we can eliminate those features which don't show up as we rotate the image. And lastly, we'll add all the information to whatever points are left. Every point will be added 64 pieces of information. And what those are, we'll see later. And why are we adding this more info over here? As I discussed, it helps us later on that we want to establish this point corresponds to this particular point in another image. So without that info, just knowing X, Y is an important point doesn't help us. Okay?
So the octaves you mentioned would be in scale space, right?
Exactly.
And what would be in rotational inverse? Did we already check anything?
I'll show you the details. Basically, will involve some hard features and computing the angles of a region. Okay. Okay, so the author says we'll assume grayscale images, but there are color extensions available. Okay, as we discuss, SURF is same as SIF. For the most part, there are actually differences, but SURF is faster, so it became a lot more popular after SIF was introduced. Okay. And the same thing we discussed, find interest points. Okay, now if you recall, when we are using the Laplacian filter, right? So we did discuss, or we did agree, Laplacian of Gaussian is a really good approach for finding those points which are important on an image, right? Okay, here's a small problem. The problem is it is computationally expensive. Okay, because as I discussed, we will be doing, scale space, applying blur, then seeing is there still, the same LOG still gives us a point over there or not. So anyway, so for this reason, what the author or the developers of SURF, what they did is, they came up with an approximation technique to LOG, okay, by using, as I will show you, box filters. As we discussed on the board, box filters are based on Haar transform, which are basically boxes. For example, one Haar transform may be sum all the pixels in the dark region, sum all the pixels in the white region, subtract the two. So anyway, how did they come up with the approximation using box filters for LOG? Let me show it to you on the next screen. Okay, so first of all, for a second order derivative filter, right, we need 4 partial derivatives, I squared with respect to x squared, y squared, xy, yx. And together, once we compose this information, this is called the Hessian matrix. Okay, and the determinant of this can give us, whether that particular point is a good point or not. Anyway, so. Okay, let me skip this part because we don't really use it. So now let's go to the approximation for a LOG filter. Okay, I think you guys in one of the assignments created the kernel. Am I right? Laplacian or Gaussian? I thought one of the things was you had to come up with the kernel.
Laplacian of Gaussian, I don't think so.
I think separately, but
Not together.
Not together.
Okay, there is a formula for Laplacian of Gaussian, and if you just go home and Google Laplacian of Gaussian kernel, it is basically a couple of exponents, if I remember correctly. So you can plug in, the +1, -1, 0, 0, -1, and come up with actual kernel. So the actual kernel on the grayscale looks like this in the LXX, LYY, LXY. Okay, but like I said, rather than using this, we will not be using it. We'll be approximating the actual Laplacian through Haar features. So here's the approximation for, so dxs xx is basically, as you can see, sort of short for derivative in the x direction, is basically the approximation to the Laplacian of Gaussian LXX filter, okay? So what are we doing over here? We are summing all these pixels. So, so this is, for example, 1, 2, 3, 1, 2, 3, 4. So 12 pixels over here will be added. The 12 pixels will be whatever is the sum, then subtracted by 2 times the sum of the pixels over here. So whatever that number gives, we come up with is the actual value of the second order derivative in the center of this calculation. Okay, so very similarly, and intuitively, does this make sense? You guys remember when we did the
It's the same we computed here.
when we did the first order derivative, right? The Sobel filter, wasn't it like this?
Yeah.
Yep.
And then plus ones are right.
So it's sort of similar. I mean, because this is a second order filter, not the first order filter. This was the first order, right? The first derivative, I mean. So anyway, intuitively it does make sense that it's going to enhance the gradient in the x direction. And intuitively it does make sense it's going to enhance the gradient in the y direction, and very similarly dxy and dyx. Okay? So in order for us to be able to compute this value, how will we do this? Will we actually sum all of these pixels?
Well, I don't see how.
Use the integral.
Okay, if we sum all of these pixels, right? How many?
Oh, with the integral image?
Integral image, exactly. So basically, this plus 1 will be computed through the 3 computations in the integral image. 3 computations, 3 computations. So to summarize, first thing you will do is whatever image is given to you, you'll compute the integral image. Correct? From the integral image, now is it easy to compute dxs, dxy, dyx, and so on? Right? Piece of cake. Okay, so anyway,
Wait, could you go back just
Go
a bit?
back.
How do you determine, so the integral image of the white region, for example, on the left, we only get the sum of the pixels if we determine the bottom right corner, but how do you determine that?
okay, so to give you an example, what's the coordinate of this, right? The coordinate of this is x of 0, y of 2, correct?
Yep.
Oh, same way, what's the coordinate of this? 1, 2, 3, 4, 5, 6, 7. So y of 7, 3, 7, right? So just like we said, you know, we called it A, B, C, D. And remember, it was the value of the integral image at D minus IA.
No, that part
Okay.
I understood. I'm saying in a regular image, how do I determine where exactly D is?
You'll be varying it over the entire image. So if you have a 100 by 100 image, in what, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's a 9 by 9 filter. So you'll apply a 9 by 9 filter
And you
over
do
here.
that on the,
Whatever result it produces, the DXS will just have one value at that point. Then you'll move this 9 by 9 filter 1 pixel to the right, and you'll get another one. So you are basically computing all the DXX. Also, of course, at the boundary, it will not show us anything. Okay. And typically, if we're taking a look at points of interest, for example, let's say.
in the boundaries.
Yeah, there's nothing in the boundaries anyway, so
Yeah.
it doesn't hurt us.
Yeah.
Okay, so by applying these box filters and moving it, all over the image, we'll be able to compute the derivative in the XX, derivative in the YY, derivative in the XY, right? Anyway, it's hard for you to probably see over here, it says 9 by 9. So the 9 by 9 filters, for example, in the Y direction, in the XY direction, look like this. But if we wanted to be more accurate, we can create 15 by 15, 21 by 21 filters, and this is how they grow. Okay. Okay, next part, the slide and explain the integral image, which we already went, so I'll skip that part. Okay, the same box filter as in the same 4 computations that we discussed. Like I called it, I think
ID.
A, B, C, D. So this was D minus A minus B plus C, right? But the same concept. Okay, so now let's pretend we went through, applied those 9 by 9 filters, the DXX. So will we get a DXX matrix? If it is 100 by 100 was the original image, this may be 96 by 96 or 90. Okay, whatever, 94 or 96 by 96, right? Same way, we'll have a DYY, DXY, and DYX. So we'll get 4 matrices, correct? After we did the integral image, applied those hard box filters by scanning over the whole image, we'll get 4 sets of data, correct? But now remember, what's our goal? Our goal is, if this is some image, let's say the image looks like this, what's our goal? What do we want to find on this image? Points of interest, right? Points of interest where Laplacian of Gaussian is the highest. But we are not using Laplacian of Gaussian, we are doing an approximation to it. So now the question is, suppose at this point it has some value. Is it a feature to keep or is it not a feature to keep? So exactly like if you go back and review the Harris corner, remember after we computed the Hessian, we put some kind of threshold to it. So basically, this is what's going on over here. So blob response will give us, like if we computed now dxx dyy minus 0.9 dxy square. So basically go through all of these and apply this formula to every one of these points in the image. Every point, apply this formula. So what will we get? And then do the determinant for this one, right? Okay, so obviously it will give us some number. Like this number may be 28.7 or whatever. Now we can put a threshold on it. If it is above a certain number, that's a feature to keep. If it is below, just discard it, right? Okay, so that's how our initial, on any given image, after we compute the dxx, dxy, dyy, apply this formula, some of these will come out to be above a certain feature, a certain threshold. So those will be our features that we wanted to keep initially. Okay. Now, what's the next step? Eliminate those features which don't show up as we zoom in and zoom out. And how do we do that? Through octaves and through Gaussian blur. Okay. So anyway, let me go to the next part now. Next part, as you can see, keep those features which still show up in scale space. And so anyway, like I said, for octave basically means reduce the image in half. In the surf algorithm, I forgot, they use 3 or 4 octaves, but anyway. Then for every octave, they'll apply 4 or 5 Gaussian blurs. So let's just take a look at this picture over here. Okay, so pretend this is one of the octaves, right? And again, octave basically means size. Like if I reduce it by 2, so reduce by half, okay, that's another octave. Okay, if I reduce by half, it will produce another octave. Within each octave, we have scale. And scale basically means, like I said earlier, Gaussian blur. So pick a different value of sigma. Okay. So let's pretend that a given octave, we applied so let's pretend this is the original image, right? We applied a sigma, high sigma, we got this value. We apply a low sigma, we got another image. Now we pick each point, and how many neighbors are for this point now? As you can see, there are 9 over here, 8 over here, 9 here, 9 here, 26 neighbors. So we'll compute again, for those 26 points, if this happens to be the highest value for our LOG approximation, then we'll keep it, otherwise we'll discard it. Okay. So as you can see, because this is a different zoom, this is a different zoom, only we are keeping it if this happens to be the higher of the other. So this will allow us to basically filter out those points which don't show up at other scales. But anyway.
So when we do zooming, number of pixels changes?
No, because zooming, remember over here, is simply applying the Gaussian filter. So only the edges will go away.
Yeah, no, actually.
But the image will still stay the same size. When we apply the octave, then it cuts down in half. So
When it gets down to the half, with the same number of pixels.
So let's say you started with 100 by 100 image, right? Okay. If you apply an octave to it, then this will become 50 by 50. Then another octave, 25 by 25. Another octave, 12 by 12.
So when we do
Within each one of these, now we will apply different sigma. And that's, so within the same octave, now we are taking a look at the zooming effect. Because the higher sigma is like more blurriness.
Okay, when we do here the number of neighbors for the after taking the filter, not for the same octave. Is that confusing?
Okay, we took the original image, right? And then we applied different blurs to it. Okay, after we apply different blurs to it, now we go to, we've already computed, for example, a few points of interest, right? In the first phase, where that formula, remember dxx minus something, that log response, where that threshold was above a certain limit. So these points were, right? As we now apply different zooming to it, now we compare whether this is still the highest of the neighboring zooms or not. If it continues to be, we'll keep it, otherwise we'll remove that. So anyway, the whole idea is to eliminate those features where there's another part over here where, because if we go to, for example, half the level, so if it was 100 by 100, we apply an octave, became 50 by 50. Okay, so then how does this point correspond to, maybe the point over here correspond to pixel value 63, right? Because we are missing the information over here, half the information is missing. But using Taylor series approximation, we can, if there was a feature that was being recognized in this octave, we can relate it to the original by using the Taylor series approximation. Okay, so let's not worry about the details. The bottom line is, even though we are reducing in size, even at the smallest level, if there was a feature that it said it's important, we can still come over here and say, okay, that's the feature. Okay, let me go just 2 more minutes so that we can at least finish this topic. Okay, last part was the feature direction. So here's where we will apply again box filters. And so what we do is we compute a neighborhood of, if this is our feature that was of interest to us, right? And then, okay, so then what we do is we apply a box filter over here. Okay, so basically at each one of these, we apply a box filter, like a horizontal and a vertical type of filter. And then we do tan inverse of whatever this divided by this, that gives us an angle. Okay. So then we accumulate all those angles and essentially, so here's an example. Okay. So for example, you can see if we add all the magnitudes, this produces the highest magnitude. So basically, this point over here has the direction is basically as indicated, because the Haar features, the tan inverse accumulation produces the highest value there. So the angle is in that direction at that point. Okay. And last part, like I said, is to generate feature vectors. So let me just skip. So in this case, there will be 64 points for each important point. Okay. So this is, okay, so anyway, this was the point of interest. We create a 4x4 window over here. Each one has 25 pixels. Then we further apply a box filter. The sum of all the dx values produces one number, absolute value produces another number. So as you can see, there will be 4 values produced over here. Okay, and there are 16 of these, so there will be 64 numbers representing this particular feature point along with the direction. So this is how later on we can do the matching. Okay, so very, very quickly, if you can just wait 1 more minute, and I'll give you the code later on. So like I said,